Hello and welcome to another class of ATMO 620. This part of the class we're talking about radiation. The last few classes we introduced some basic concepts that regard electromagnetic waves and radiation in general. We talked a little bit about vibrational modes and rotational modes and why we observe certain kinds of spectra and how atoms interact with photons and electromagnetic radiation in general. Last time we talked about sort of atmospheric spectra a little bit more. And today we will introduce a very, very important topic, which is pretty much I wouldn't say the main point of this part of the class, but it's one of the focal points of the radiation part. And the topic I'm referring to is, of course, radiative transfer. Now, radiative transfer is a concept that is not specific to atmospheric sciences, and it's something that exists in many different disciplines. In general, it refers to the transfer of energy through atmospheric radiation within some kind of medium, okay? And for us, it means what happens to photons as they cross the atmosphere, either coming from above, from the sun, or coming out of the Earth as long-wave radiation, okay? But you could imagine radiative transfer to be applicable also in other contexts. For example, every time you go and take an X-ray at the hospital, and hopefully that's not very often, but every time that happens, that is an example where radiative transfer is used. The problem there is, or the problem that the doctors, well, the technology, let's say, the technology of X-rays is based on the observation that different tissues in your body and different organs in your body absorb radiation differently. Particularly, obviously, your skin absorbs long-wave radiation and visible light. But photons that are energetic enough, so it's called the X-ray part of the electromagnetic spectrum, these could potentially travel undisturbed through your body. Certain organs absorb those X-rays. I'm thinking about bones, for example. And so when you look at an X-ray, what you're doing is you're shooting X-ray photons, high-energy photons through your body, and you're collecting on the other side those X-rays that were not absorbed or scattered. And so knowing that your stomach doesn't absorb photons, but your spine does, allows you to use this technology or this observation and observe the spine. And so you can look at whether the spine has some damage and whatnot. That's why X-rays are used, among other things, to diagnose, for example, if there's a broken bone, okay? So radiative transfer, in other words, is something that is not just useful for atmospheric sciences. And when we talk about radiative transfer, we're really including many different processes in this category. Okay, what influences radiative transfer is processes like absorption of photons or emission of photons through the atmosphere, in our case, or even scattering. Scattering, I remind you, is the deviation of photons by matter. Now, before we dig into this topic a little bit more, I just wanted to introduce some concepts that are useful. The first concept these are mathematical concepts, but they will be useful to understand what we will discuss today. The first concept that I want to introduce is that of a solid angle. To make a long story short, solid angle is the generalization to 3 dimensions of the concept of an angle. So in 2 dimensions, in good old Euclidean geometry, let's say you have a circle, and the circle has a center here, and the circle has a certain radius. Excuse me. Sorry, I hurt my hand, so it's kind of hard to draw and kind of painful. But anyway, so this is the radius r. Okay. And let's say you consider a portion of the circumference, and this portion has some length L. Okay, we can draw another radius here. Now, by definition, this quantity, this the width of this is what we define as an angle, and quantitatively, this is the length of the circumference of this segment of circumference over the radius of the circle. Okay. What is the angle of a full circle? Well, the L in this case will be equal to the entire circumference, and in that case, so A of the whole circle will be, the circumference will be 2 pi r, of course, divided by r, and that would be 2 pi. Obviously, the units of measurement in 2 dimensions, like here, are radians, and so 2 pi radians is the measure of the whole circle. Something similar holds for 3-dimensional stuff. And so imagine you have a sphere. Okay, now I don't know how to make this quite 3D, but let's say this is a sphere. And on the sphere, you can cut in the area, and this area has width dA. Okay, let's say that this is a small enough area. Sphere has radius r. And you can define a solid angle, d omega, as the small area divided by the square of the radius now. Units of measurements are not radians, but they're steradians for solid angles. What is a solid angle of the whole sphere? Well, substitute dA with the whole area of the circle. That is, I remind everyone, 4 pi r squared. If we divide by r squared here, this is 4 pi. 4 pi is the solid angle corresponding to the entire circumference. Okay? Excellent. Now, another useful concept, or another useful thing that we might want to keep in mind, I don't think that we'll be using this thoroughly, but I thought this could be useful, is to write down the solid angle in coordinates, and in particular in spherical coordinates. When you are dealing with some kind of generic problem, usually it's a safe assumption to use Cartesian coordinates, x, y, and z. Okay. An area in this coordinate system can be written as dA equal to dx times dy, right? This is a small area, 2-dimensional area. When you're dealing with a problem that has some kind of a symmetry, then it's probably a good idea to use a coordinate system that reflects that symmetry. In this case, let's suppose that our system has some spherical symmetry. What is an example of that? Well, imagine that you have a sun that is emitting photons in all possible directions, and it is emitting the same amount of photons in any kind of direction. Okay? This is a typical example of a spherical symmetry. And therefore, it makes sense to use what we call spherical coordinates, which are more natural coordinates. There is a transformation that lead you to dx, to x, y, and z, to the coordinates on a sphere. And in particular, we use three coordinates on a sphere. The first is the radius, meaning the distance from the center. Then we use an angle that tells us how high we are on the horizon. So the first one is the radius. Then we have an angle that tells us how high on the horizon we are. And that angle is theta. Okay. And finally, another angle that tells us where exactly on this longitudinal circle we are, and that angle is phi. So, this is essentially the same as r is the radius, but then theta and phi is essentially the same as longitude and latitude. Okay, theta is latitude in our system, and phi is longitude. If you do all the transformations, then d omega, you get to the result that d omega equals the sine of theta, which is the elevation from the horizon, the latitude, times d omega times d phi. The sort of the width of this circle. It kind of, and theta goes from 0 here at the zenith to pi at the sort of north pole. When you're looking up, it's 0. When you're looking down, it's pi. It kind of makes sense that it's sine of theta, because if you are on this wedge here, right, the closer theta gets to 0, the smaller this area is, right? If you took the same area here, even with the same d theta, but you're getting closer and closer to here, so this aperture here, the segment here gets smaller and smaller, and so the closer you get to the vertical axis, the smaller the area becomes, and so it kind of makes sense that it's proportional to sine of theta. Same thing happens if you go to the South Pole. Also, interestingly, but not surprisingly, if you integrate over all the sphere, over all the d omega, that means 0 to pi d phi and minus, 0 to theta sine theta, that will give you the 4 pi that we know is the solid angle of the entire circle. Okay. Now, having defined what a solid angle is and having given some sort of a refresher of how to compute them, let's start talking about one of the main characters for today, and that is the spectral radiance. Suppose you have some body, a black body or a gray body, whatever. This body is emitting photons in space. Photons have some frequency, and let's say that the frequency is within a range between nu and nu plus d nu. Okay? Let's say that these photons, imagine an array of photons that is coming out of this body, and they're coming out of an area, infinitesimal area dA. They're coming out with the direction s, and the ray is contained in a cone of solid angle d omega. Okay, the power that goes through this surface dA in a time dt, okay, in a cone d omega within this frequency band, is what we call spectral radiance. Okay. So spectral radiance is the power per unit area, per unit solid angle, per unit frequency interval in a direction of a unit vector s. Okay. If the body is emitting everything isotropically, meaning that it's emitting in any direction in the same way, then the spectral radiance is exactly Planck's function that we introduced before. Okay, and it's simple, it doesn't depend on angles, and has a relatively innocent looking mathematical formulation. The units of measurement of spectral radiance are watts per meter square pairs to radian per hertz. Okay, this is the power. This is per unit area, per unit solid angle, and per unit frequency. Okay, so it kind of makes sense. Now, it may be the case that you're not really interested in the power per unit frequency. And so maybe you just want all the power that is emitted regardless of the frequency. So you want to sum over all the frequencies. In that case, you take spectral radiance, you integrate over all the frequencies, and you obtain a quantity that is called radiance. So radiance is power per unit area per unit solid angle, okay, considering all the frequencies. It may be, on the other hand, that you're not particularly interested in a particular solid angle. So maybe you want to integrate over all the possible solid angles. In this case, you obtain, you're integrating over all the solid angles, and you obtain something that is called spectral irradiance. Obviously, you need to take into account the fact that if you are considering, let's say that you have your beam, and you're considering all the different possible solid angles that come out of this area dA, okay. In order to take all these contributions into account, you need to take a cross product between, let's say that n is, sorry, I'm not drawing this correctly. Let me redraw it. Suppose that you have, this is your sphere, and the sphere has a vector of unit length that is perpendicular to the surface of the sphere, and we call this n. And now you're considering any kind of beam that is coming out with a generic angle s. Before, we were considering something that was just coming out in a direction that was, in the drawing before, the direction looked like it was exactly parallel. S looked like it was exactly parallel to n, but there's no need for that. It could just be a more complicated scenario. Now you're integrating over all these possibilities, okay? And when you do that, you need to take into account the fact that these have different directions, and so you need to take a cross product with the vector that is perpendicular to the surface of the area of the sphere that you're considering. Okay, this we call spectral irradiance. Okay. Finally, it may be that you're interested in the irradiance, but without caring about a particular frequency, and so you take the spectral irradiance, you integrate over all the frequencies, and you get what we call irradiance. So spectral tells us that we care about frequencies, and lack of spectral adjective here means that we're integrating over all the frequencies. Radiance means that we're considering just one beam of light. Irradiance, it means that we're considering all the possible beams of light that are coming out of the surface with any kind of angle. Of course, the fact that there is a cross product between the vector that is normal to the surface of the sphere and the beam of light, S, means that the irradiance has, spectral irradiance and irradiance have an orientation. So if there's a beam of light that is coming out of the surface, then this cross product will generally be positive, okay? And if the beam of light is coming in, because the vectors are directed in the opposite direction, this cross product will generally be negative. We denote the first case we will denote with an upward pointing arrow, and the second case with a downward pointing arrow. Okay, and this could be, for example, if you want to think about the surface of the Earth, or if you want to think about the Earth and the atmosphere, this could be the flux of photons that are coming in from the sun, sort of high energy photons that are coming in from the sun, and they're coming down towards the surface of the Earth. They're penetrating the atmosphere and coming down. This F upward could be the long wave photons that are being re-emitted by the surface of the Earth, and these are going up. Okay. The difference between the two is what we call the net power per unit area. This is bringing energy in, this is taking energy out. If you take the difference between the two, you get whatever is left. The energy, the power that is deposited in the atmosphere. Just to give you a cartoon representation of what I just said, the difference between radiance and irradiance. Radiance, you care about one particular beam of light. You know, what is the effect on this ball here of this particular beam of light? Irradiance means you're summing over all the possible beams of light that are coming down. Okay. Also, if we're considering a particular surface that has a certain temperature and emits like a black body, the spectral radiance will obviously be given by Planck's function, almost by, I wouldn't say by definition, but it's kind of intuitive, right? If you remember how we defined Planck's function. The irradiance, how that be defined? Well, the radiance doesn't really, the spectral radiance doesn't really depend on the solid angle in Planck's function, right? So you can just take this out of the integral, and you could simply integrate, suppose that you're considering all the emissions in sort of the northern hemisphere, then you're just simply taking the integral over all these angles, and what you obtain is that actually the spectral irradiance is again proportional to the Planck's function, with some proportionality constant, of course, but it's proportional to the Planck's constant. What about the irradiance? Well, the irradiance would be this stuff integrated over all the frequencies. Now, B nu Planck's function now depends on the frequencies, and you can solve the integral, and you actually find our good friend, the Stefan Boltzmann law. Okay, Stefan Boltzmann law told you that the power per unit area was proportional to the fourth power of temperature, and if you actually integrate that, this is exactly what you obtain. Okay, so these were a little bit of preliminary considerations that we needed to get into today's topic, and now we can finally look at today's topic, radiative transfer. The main problem of radiative transfer is that you have some kind of a medium, okay, whatever it is, be it atmosphere, your bones, or whatever. And this medium has a particular, you're considering a particular width ds. You have incoming radiation that has spectral radiance L nu. The radiation goes through the medium of width ds and comes out with nu spectral radiance L nu plus dl nu. How much is dl nu? You know, is it positive, is it negative, and how can we write this down? Well, first of all, I want to introduce a concept that will be useful for the rest of the class. And this is what we call the extinction coefficient, the extinction coefficient. So suppose that you have a beam of photons that is coming into a medium. Okay, some of these will be eventually scattered, some of these will be absorbed. The extinction coefficient is a number that quantifies essentially the fraction of photons that come in from A1 and will not make it through A2. And it kind of gives you an idea of the attenuation of the beam as it goes through a medium. Okay, when you turn on a torchlight and you point it towards your arm, okay, the photons will will actually penetrate your skin, but they will not penetrate very particularly deeply. Okay, the extinction coefficient tells you, in a way, how deep can they penetrate before they get absorbed, or in a way, if you take a millimeter of your skin, what is the fraction of photons that is absorbed or scattered from your skin? Okay, so we'll indicate this with K nu. K nu will depend in principle on frequency. If you shine visible light through your bones, that will have some extinction coefficient. If you shine a gamma ray through your bones, that will have a different kind of extinction coefficient. Okay, probably blow your arm up, but anyway. So the main result of today's class is what we call the Beer-Lambert Law. The Beer-Lambert Law tells us exactly how to compute that dl nu, meaning how much is the beam, what is the change in the spectral radiance of a beam of photons that is entering a particular medium. So let's suppose that you have a medium and this medium have extinction coefficient k nu. Let's say that this is even dependent upon the position where you are. Okay, so let's say this is the medium. Let's say that this has some width ds, okay? And s is a coordinate that tells us where we are in this medium. The medium has extinction coefficient k nu, has some density, rho of s, okay? And the light is coming in with spectral radiance L nu of s, okay? It's coming in and it's coming out. That nu plus dl nu, where Beer-Lambert law says that dl nu equals minus, so in principle, it will get extinct as you go through the medium, minus the extinction coefficient, times the density of the medium, times the spectral radiance itself. Okay, so the decrease in dl nu will be bigger the bigger the initial spectral radiance, times ds, the width of this medium. Now, this is non-trivial because it establishes a very simple relationship between the extinction, essentially, and all the other parameters. Notice that L nu, for example, comes in with a linear power, which turns out to be a very lucky thing because it will allow us to solve things quite easily. Here I just wanted to show you a little bit more of the extinction coefficient. The graph here, this shows the extinction coefficient for liquid water. And notice that the absorption, this is in logarithmic scale in both x and y. Notice that in the visible light, the absorption has a minimum, which turns out to be a lucky thing for us because it makes for a great day at the beach. The ocean is clean, you can see inside, right? But actually, liquid water turns out to be pretty opaque to ultraviolet radiation and also to infrared radiation. Okay, so in general, extinction coefficient will be highly dependent upon the frequency that you're considering. Also, notice that yes, you could derive these quantities in a very rigorous way with a lot of math, but more typically, people have some more sort of a heuristic approaches and derive these with sort of more heuristically, just maybe with observations and experiments. Okay. Now, one important thing is that yes, there is absorption and scattering as the beam of photons travels through a particular medium, but it could also be that the medium itself may be generating photons for whatever reason. Maybe it's a radioactive medium. Maybe, like the atmosphere, produces some photons for whatever reason. Or maybe they're coming in from outside. I don't know. But the point is, you could also have not only scattering of the beam of photons or absorption of the beam of photons, you could also have emission. And so we need to take that emission into account and modify the Beer-Lambert law accordingly. The way to do that was introduced by Schwarzschild in 1914. Schwarzschild is better known in physics for being, the person who introduced the concept of event horizon, solving Einstein's equation. But in 1914, Schwarzschild introduced this new concept and kind of modified the Beer-Lambert law. This is sometimes called the Schwarzschild's equation, but essentially, this is Beer-Lambert law divided by ds, if you will, with the introduction of this new term. Notice that L nu appears with a minus sign, but J nu, this kind of a source function, appears with a minus times minus plus sign. Okay, so dl over dz, so the change in spectral radiance within the path, is as a negative term that is due to the extinction, but also positive term that is due to this source function. If we were considering infrared radiation, if we were considering the radiative transfer within the atmosphere, then we'd have to take into account the fact that the Earth is emitting infrared radiation, okay, at a particular temperature. And in that case, we'll have to consider the source function will be the source function that produces this infrared radiation, and that is, luckily, it just turns out to be Planck's function for the temperature that is the temperature of the surface of the Earth. Okay. One concept that is quite useful to introduce is that of an optical path. Now, let me remind you, this is Schwarzschild equation, right? S equals minus K nu rho of A L nu minus J nu. This is okay, but it looks still kind of cumbersome. So one might wonder, is there a way to absorb this K nu rho A somewhere so that they just disappear? Well, you can divide by these and you obtain dl nu over K nu rho A ds. Define a new quantity called chi nu, and this is defined such that the differential of chi nu is exactly K nu rho A ds. This is what we call optical path. With that, Schwarzschild equation simply becomes derivative of L nu with respect to chi nu equals to minus L nu minus J nu. Now, this is introduced as a differential, so you could actually also introduce it as a, if you want the definition of chi nu, you have to integrate this, and if you integrate this, then you obtain this expression. Okay. So what does the optical path really correspond to? Well, let's think about this. Suppose that you have some medium here, and the medium has width ds. Okay. Now you have, this is the width. Now you have a beam of photons that is coming in. Let me draw the photons. A beam of photons that is coming in, okay, in this medium. Now, if you ask me, these guys, some of these will be scattered, some will be absorbed, and some will make it through. Okay. If you ask me, what is the distance traveled by this light beam? Well, technically speaking, from here to here, technically speaking, it would be ds. Okay. But for some photons, the distance traveled is actually, the answer to this question might be a little bit trickier. Let's take, for example, the case where the extinction coefficient, for example, is 0. Okay, so let's suppose that, let me remove this and this. So extinction coefficient is 0, meaning that the material is transparent. Okay. If you ask me, what is the distance traveled by these photons within this material? Well, the answer physically is ds, but in a way, it's kind of 0, right? Because it's almost as if these photons hadn't even realized the fact that they were inside of material. It's a bit like in Wile E. Coyote's cartoons when, the coyote is chasing the roadrunner and suddenly he finds himself off a cliff, and the coyote doesn't fall until he realizes that he is going to fall, right? And it's kind of the same thing here. These photons are going through this medium, but they didn't even realize that they were going through a medium because the extinction coefficient was 0. Likewise, it might be that this medium is maybe a crystal where the atoms of the crystal are so far apart that photons can go through the medium barely without noticing that there's anything. in this medium. Okay, and so the physical path, yeah, sure, it's ds, but if you cared about the path in terms of the likelihood that photons are absorbed or scattered and whatnot, then that distance is kind of zero. And that is precisely what the optical path measures. Okay, so the actual physical path is df, but the quote-unquote optical path is zero in that case. And that's why the optical path depends on the extinction coefficient and the density. Okay. Okay, can we solve now, if we look at Schwarzschild's equation, dl nu d chi nu equals to minus L nu plus J nu. Sorry. Can we solve this equation? Well, or can we find some generic solution to this equation? Well, the answer is yes. Let's start by taking this L nu and bringing it to this other side, and we get to this equation down here. Does this look like something we can do something about? Well, let's multiply this equation by e to the chi nu, both terms. And so let me do it up here. There's a bit more space. So we'd have e to the, I'm going to drop the nus just because I want to make my life simple. But remember, everything is still dependent upon frequency. dl chi plus L equal e to the chi j. Okay. Now, let me ask you this. What is the derivative of e to the chi times L divided by, with respect to chi? Well, it would be the derivative of the first term, and the derivative of the first term is, this is an exponential, so it's just itself, times L, excellent, plus the first term times the derivative of the second, dl d chi. Let's collect the exponentials, e to the chi L plus dl d chi. Well, but wait a minute, this guy here is exactly this guy here. So we can rewrite that as a total derivative. d e to the chi L d chi equals e to the chi j. And now this is easy because now you just integrate within in d chi, and this is easily solved. And you get precisely to this guy here. Okay. The integral of a derivative, it's just the argument of the derivative times this integral, right? That is more complicated now. Plus a constant, obviously. We could find the constant if we just say, for example, that at a particular point as 0, the spectral irradiance has to be L nu 0, then you get to this generic solution. Now, this is pretty neat because it tells you the spectral irradiance at any point within the medium. So this, it's solved, like it's done. Where's the trick here? Well, the trick is that it's not really solved now, is it? Because J nu, we don't know what it is, and it might actually be an extremely complicated function. And so it may not be as simple as you might think at first to solve this integral. But you know what? Whatever. You could plug this in a computer, and the computer would solve that for you. Okay. Interestingly, without any kind of emissions, this term would obviously go to 0, and you just find that the spectral radiance would decay exponentially with the optical path, which is kind of obvious if you think about it, if you think about Beer's law. And essentially, the optical path gives you the e-folding scale as your beam goes through the medium, the e-folding scale of the spectral radiance. We distinguish two different limits when we talk about optical paths. The first limit is what we call an optically thin region or medium. This happens when the optical path is a lot smaller than 1. What this means is that the photons are weakly interacting with the medium, and therefore they can just go through. The medium is almost transparent to these photons, or for these photons. The opposite region is when the medium is opaque for these photons, and we talk about optically thick medium. Ultraviolet radiation that comes in from, visible radiation, for example, that comes in from the sun, the atmosphere is optically thin to that kind of radiation, right? We do see colors, likely, and photons in the visible range. But long-wave radiation that is re-emitted back from the surface of the Earth, the atmosphere is opaque to that. And that is essentially the greenhouse gas effect. And notice, this is just a curiosity for a trivia night, but notice that even though the sun is what is emitting all the photons, and the photons are produced in the core of the sun itself is optically thick to these photons. The reason is that the sun has such a high density that photons are constantly being absorbed and re-emitted, absorbed and re-emitted, absorbed and re-emitted. And it's estimated that it takes about 100,000 years for a photon to be produced in the center of the sun and emerge from the sun. So the light that you're seeing right now, if you open your window, look at the sun, unless it's nighttime, in which case, well, I guess you could look at the moon. But the light that you see right now was produced 100,000 years ago, more or less, okay? So it's quite an interesting fact. Now, a very simple solution, well, not really solution, but a very simple case is a case in which your medium is kind of uniform, and the extinction coefficient and the density of the material are kind of uniform and don't depend upon the particular point of the medium where you are. In that case, the optical path, d chi nu equal k nu rho a ds, well, you could just integrate both terms, right? And because these are not dependent on the particular position where you are, you'll simply have the chi nu equals to k nu rho a times s, okay? And so you can substitute this back into the solution to the Schwarzschild equation, and you arrive to this expression here. Generally, this expression can be interpreted, these two terms can be interpreted pretty simply. The first term here, we talked about this in the context of the Beer-Lambert Law. This is the radiance that gets attenuated because of the extinction as you travel through the medium. This term here contains the source function, and this is the radiance that you gained from the emissions. The radiance that you gained at a point S, okay, from the photons that were emitted at a point S prime, okay? And here you're summing over possible S prime. So imagine that you are, this is the origin, this is S where you are, and you're in the medium. Now the beam of photons has to go through all this path, okay, from 0 to S. And within this path, it may have gained some photons because of the emission, okay? And so you're saying, okay, let's pick a position S prime. How many photons did I gain here? J nu would tell you that. Okay, so you start counting. And then you sum over all the possible positions, all the possible S primes, okay? All this sum is the entire contribution that you got from these added photons, and it's exactly what this integral measures. Okay. Last few slides, I wanted to mention a couple of things. First, if you remember, at the beginning we talked about Kirchhoff's law that said that at local equilibrium, the emittance and the absorptance of a medium had to be the same. Now, remember that the spectral emittance we define as the ratio of the emitted radiance to the radiance that was emitted by a black body, okay? let's say that the black body had had some kind of a density rho A. Rho A times ds measures essentially the mass, okay, in this one dimension of the material. K nu is the extinction coefficient. The emitted radiance is given by this term here. Okay, so it's J nu, which is what is sourced by whatever, by the black body, times whatever is sort of attenuated, and this is divided by the radiance that is emitted by a black body. So this is the spectral emittance. Okay, the spectral absorptance is the fraction of incident radiance that is absorbed. So what is absorbed is, again, proportional to what is coming in, L nu, times the absorption coefficient, times obviously the width and the density of the material, divided by the incident radiance, that here we're just calling L nu. Notice that L nu and L nu here simplify. So the absorptance is simply K nu times rho A times ds, and it doesn't depend on the spectral radiance. At local equilibrium, by Kirchhoff's law, the spectral emittance and the spectral absorptance have to be the same. And if you equate epsilon with alpha, then all these terms simplify, and what you're left with is that the source function has to be the Planck's function. Okay, very final thing for today. So radiative transfer is a simple concept, if you will, but solving spectral radiative transfer equations may actually be really complicated, okay? And approximations are often needed. One case in which approximations are needed is the fact that if you consider the planet, okay, we have a spherical planet and radiation is coming in from the sun, so it's coming in potentially at some angle, and it's kind of re-emitted in each position. It's kind of re-emitted in all directions, okay? So you have all these rays that are coming in and going out at all crazy angles. This means that if you want to solve these equations, you have to solve crazy complicated solid angle equations, and unless you're John von Neumann, these are really complicated equations to solve, okay? Even for computers, actually. And so one way that we often simplify our life with is to assume that essentially the photons that are coming in are coming down with a straight angle perpendicular to the surface, and what is emitted back is going back with perpendicular direction, okay? Now, if you were to use the irradiance, or the spectral irradiance, or the spectral radiance actually, if you were to use the correct spectral radiance values for these particular perpendicular directions, then you would miss all the photons that are coming in at an angle and those that are going out at an angle, okay? So what you want to do is modify, if you want to resort to this approximation, you need to modify the fact, you need to modify the value of the spectral radiances in order to account for whatever is lost, okay? And you do that by introducing an effective optical path, if you will, okay? This optical path is called chi nu star, okay? And this is equal to 1.66 chi nu, okay? So it's a scale optical depth that takes into account the fact that you are actually considering photons that are coming in or out at different angles, okay? So, I mean, these are unfortunately things that you have to do if you want to solve these very complicated equations. These are things that you have to do. We will not be doing a lot of crazy calculations in this portion of the class because they will be too complicated to do. But just keep in mind that this is an approximation that is often made. Okay, I think this concludes what I had to say for today's class. Please let me know if some things were unclear. We introduced some concepts like solid angle and some mathy stuff. So I don't know if everything was clear, but if it wasn't, let me know, and I'll be happy to answer any of your questions. Otherwise, I will see you in our next class. Thank you very much for listening. Thank you very much for listening. Can't remember how to speak English anymore. Well, anyway, bye.